So now that I've already explained basically what we're doing with Euler's method and forgot to record, I'll just briefly repeat it again, but I'll draw a picture this time to make it even better. So suppose we're given our differential equation, and we're given some starting value. Let's say, I don't know, it doesn't really matter where it is. Let's just say it's right there. And we will use our x and our y values here. So this will just be some initial condition, x, y. And we will find dy dx to be, you know, whatever value it might be at x comma y. Suppose it has a slope of, you know, 1 at that with those x and y values. So we'll draw a little line segment with a slope of 1 up to, you know, x plus 0.1. Suppose that that's our step. So we'll have a new point that'll be x plus 0.1 and y plus dy dx evaluated at x being 0.1, or sorry, x being x and y being y. So we'll just say y plus dy dx. And then we'll find the next slope at this point, which may be a little bit larger. And so we'll go up to x plus another 0.1. So x plus 0.2. And we'll get some other y value there. And it'll be whatever our original y was plus this first change in y plus a second change in y given our new point x plus 0.1 and y plus that first dy dx. And we'll just keep following this process until we get to the x value we're interested in and finding the value of our function at. Does that sort of make sense? Or no?
Yes, it does.
Okay, yeah. Basically, all we're doing is we're finding the slope at each point, you know, drawing the line segment over whatever x interval we want that, you know, will be given to us what x interval to use, then finding the slope at that point, and then drawing the next line, and then finding the slope at the next point and continuing on. So let's see if we can do this. So we're going to be given the differential equation x plus y, and we know that f of 2 is equal to 0. And we're going to use Euler's method with a step delta x equal to 0.2 to approximate f of 3. And you're probably going to want to use your calculator to do some of this approximation here. And this is how I would normally set this up. I normally make like a little chart. So I'll have a column for my point, whatever x, y is. I'll have a column for the value of my derivative at that point, which is x plus y. I'll probably just throw in one other extra column to remind me every time that I need to multiply it by delta x, which is 0.2. I'll have a column for my delta y, change in y, which is always going to be delta x, how much we change the x by that slope. And then I probably don't need an extra column. I guess I could put this last column here at the end for the new point x plus delta x and y plus delta y, if we wanted to. If you don't want to make that last column, you can always just, once you get delta x and delta y, add them to your point and then just put it in the next column down. In the past, I found that that's helpful for people to have it in there. And so all you'll do is just go through for each one of these. So what's our starting point?
Two comma 0.
2 comma 0. So what is dy dx if it's x plus y? Should be what's x plus y if x is 2 and y is 0? X plus y is 2. And our delta x is always just going to be that 0.2 value, since that's what we were told in the problem. What's our delta y going to be then?
.4.
0.4. And so our new point that we're going to use is x plus delta x, which was 2 plus 0.2. And then y plus delta y, which was 0 plus 0.4. So at 2.2, it's going to be about 0.4. And so that will be our next starting point that we're going to use, 2.2 comma 0.4. And what is x plus y now?
2.6.
Okay. And if our delta x is 0.2, what's our delta y going to be?
0.52.
And that gives us a new x plus delta x value of 2.4. And our y plus delta y should be 0.4 plus 0.52, which will be 0.92. Good or not? And it starts to get a little bit annoying with the arithmetic now, but conceptually it's the same. It shouldn't be too difficult. 2.4 plus 0.92 ought to be what? Should be 3.32. Our x is still 0.2. What's that going to give us? That's going to give us a 0.664 there. And that's going to give us an x value of 2.6 and a y value of, what does that add to become? 1. Let's see here, 1.584, looks like. Does that seem right to you guys?
Yes.
Oh, good. And that'll be our next point. Isn't this fun, everyone? And what's our x plus y now going to be? 4.184. And then our delta y here should be what? 0.8368? That seem right?
Yes.
Giving us 2.8 and what does that add to? 2 point something, right? $2.4208. All right. And then one more to go. Let's see what those have to become. 5.2208, I think. And that should just be 1.04416. Giving us a final value of 3, comma what? 3.46496. Hopefully, somebody check my arithmetic just to make sure, but pretty sure that's right. And so that's our approximation for f of 3, given that differential equation with the initial condition using a step of 0.2. A little irritating and time consuming, but not inherently too difficult, I don't think. Do y'all agree? Yeah, so if you use the smaller the steps, the more accurate it gets, for sure, because then you're taking even smaller and smaller linear little pieces, and the smaller the linear piece, the more it resembles the actual function, Aiden. So yeah. Also, Aiden, I don't know if you saw my email, but that allowed me to submit when I checked last night, so should be good now.
Oh, okay, great. Thank you.
Yeah. All right, anybody questions on that? Everybody feel okay about that? Pretty straightforward. Let's do one more just to make sure we got it. This time we're going to go from x equals 2 to x equals 1.5. So we're going to go to the left, which means our delta x is going to be negative each time. We want 5 equal steps. So if we're going from 2 to 1.5, our steps should be what? What should delta x be every time? Negative 0.1. So let's set up our nice little chart here. So we got our point, x, y. We've got our dy dx. This time that's equal to 2x minus y. We've got our delta x, which we know is always negative 0.1. And we've got our delta y, which is equal to delta x times dy dx. And we've got our new point, x plus delta x, y plus delta y. Nick, delta x is whatever we're changing each time. So we need to go from x equals 2 to x equals 1.5. And it says we want 5 equal steps. So we got to go down by 1/10 each time to have 5 equal steps to get from 2 to 1.5. And we're starting with what point? 0.2, 3. And so what should dy dx be the first time? One, which means delta y should just be 1 times negative 0.1, so negative 0.1. And our first point here should be 2 minus 0.1, so 1.9, and 3 minus 0.1, so 2.9. And what does our dy dx become for the next one? Should be 3.8 minus 2.9, right? Which is 0.9. Delta x is negative 0.1 again. And multiply those together. What do we get for our delta y value? Negative 0.09. And so we now go down to 1.8 and 2.81. And what do we get now for our dy dx? Should be 0.79, I think. You guys agree with that? Which means negative 0.079 here. And what's that going to give us? 1.7. And what do we get if you subtract those? 2.731, I believe. Does that sound right to everybody? And what's your next dy dx? 3.4 minus 2.731. So that'd be what? 7/10 minus 0.3. That should be 0.669. You guys agree with that or no?
Yes.
Oh, good. And multiply that by the negative 0.1. We're now one step away. Let's see, the 2.731 minus 0.0669. What does that come out to be? 2 point what? $2.6641, I believe. Oh, good. I can still do arithmetic. I feel good about that. And then 1.6, 2.6641. What is that going to give us? What is it?
0.5359.
Negative 0.1 makes that negative 0.05359. And our answer is at 1.5, we should get whatever that is when you subtract those. Hopefully I subtracted that correctly. If not, let me know, I can fix it. But everybody good with that or no? Wonderful. All right. So that's the whole idea of Euler's method. There's not anything else to it. It's just another way of approximating the solution to a differential equation numerically, rather than having to actually sketch out a graph of the slope field. You will undoubtedly have to answer one or two questions where you have to use Euler's method on the AP test. Usually it's in a free response question, like included with some other differential equation or slope field or separable differential equation or something like that. So we'll see some of those when we start doing our free response review in a week or two here. All right, we good to move on to separable differential equations? All right. I'll take that as a yes. So when we talk about separable differential equations, this is not the one I want. Actually, that's fine, yeah. All right. When we talk about separable differential equations, we're talking about a dy dx equals some function in terms of y times some function in terms of x, or it could be a quotient of the two functions. Either way, what we want to be able to do is we want to be able to separate it so that all the y's are on the left-hand side with the dy, and all the x's are on the right-hand side with the dx that will move over to the right. And once we have all the y's with the dy and all the x's with the dx, we can just anti-differentiate both sides. And if we do that, we should end up with a nice little equation in terms of x and y that we should be able to solve for y. And one thing to remember is that when we do this, and when we do this integration, we get some, we'll call it capital F of y plus some constant equals, we'll call it capital G of x plus some other constant, right? Now we don't actually need to write the constants on both sides, because we could just say, well, whatever we get in terms of y on the left is equal to whatever we get in terms of x on the right, plus some other constant where that constant is equal to the other constants, the difference between the other two constants. So traditionally what we'll do is we'll just write the plus c on the side with the x terms. Everybody good with that conceptually, what we're going to do? Perfect. I'll assume that's a yes. So let's start with a nice easy one here. We're going to solve for y. If dy dx is x times y squared. And then we've got y equals 1 when x equals 1. So we've got an initial condition, and it's a separable differential equation. It's a product of x and y. So we'll be able to separate the variables, integrate, and solve for that constant. So what should we do first? Okay, yeah, so get the square to both terms, right? Yes, Adrian, and then we'll divide by the y squared. So we'll have dy dx equals x squared y squared, and then dy over y squared equals x squared dx. Everybody good with those first two steps? So get the squared into both terms and then separate the variables. Okay, and how do we integrate dy over y squared? It's not natural log absolute value y squared, right? It's just a simple power rule problem. What's the integral of dy over y squared? Negative 1 over y, good, Nick, equals x cubed over 3 plus our constant. And so we'll plug in, and some teachers will tell you solve for y first, then find your constant. I think it's easier to just plug in your initial condition immediately after you integrate and then solve for your constant. So plug in 1 for y, that side's negative 1, this side's 1/3. So our constant is negative 4/3. So we'll then go and rewrite this with that constant. And in order to take the reciprocal of this, right, which is what we'd like to do, I have to combine everything over here into a singular fraction. Right, so if I want to take the reciprocal and just get negative y, I've got to make this x cubed minus 4 over 3 and then take the reciprocal of that. If you don't combine them together and you just take the reciprocal of each fraction separately, the answer you get is horribly, horribly, horribly wrong. So make sure if you're taking the reciprocal of both sides, you have only one single fraction on the right. All right, and then we divide by the negative 1. We should get y equals, well, negative 3 over x cubed minus 4. And is that a good answer for us or no? No, it's not. Why is that not a good answer?
Because the denominator can be equal to 0.
Right, we have to look for the interval of validity. So x cubed minus 4 can't be 0, tells us that x cannot be the cube root of 4. So we have one single value that we have a discontinuity at, which tells us that the domain itself is negative infinity to the cube root of 4, union cube root of 4 to infinity. But then we need to look at our initial condition, x equals 1, and think about where that falls. And so does 1 go between negative infinity and the cube root of 4, or between the cube root of 4 and infinity? That should be an easy question for you to answer. Should be between, yeah, the negative infinity, right? Because cube root of 1 is 1. So cube root of anything more than 1 is going to be more than 1. So negative infinity to the cube root of 4. So we'll use this piece. So don't forget about your intervals of validity on these. Any questions or issues with that? All right, let's do another one. dy dx equals y over x. So what should we do? Nick, no. So if I go back to the last one, we can't put brackets on infinity ever, and we definitely can't put brackets on the cube root of 4 either, because that's where our discontinuity is. So we can't, we can't include cube root of 4. It's got to stay as an open interval. Does that make sense? Okay, cool. All right, so next one. dy dx equals y over x. So what's the first step there? Separate the variables. So dy over y equals dx over x. Everybody agree with that? And then we'll integrate both sides. Integral of dy over y is natural log absolute value y. Integral of dx over x is natural log absolute value x plus our constant. And two things we need to do right here. As soon as we start integrating, we got to think about if this original equation that we get from our integration has any discontinuities in it. And so we'll immediately say, because of this, x cannot be 0. Everybody agree with that? So this is something we'll have to take into account all the way through, even if, as we solve this for y, our final equation doesn't have this discontinuity, we still have to use that discontinuity in it, right? It's just like if you were graphing something like x squared minus 4 over x minus 2. This is the equation that we are graphing, just because you go through here, factor it, and no longer have a discontinuity at 2, you still have to include that whole at x equals 2, right? The same concept here. There is no value that we can use there for x equals 0. And so at the end, we'll have to take that into account. Other thing we got to do is plug in our initial condition. Natural log 2 equals natural log 2 plus our constant. So our constant is 0. And so we'll just go with natural log absolute value y equals natural log absolute value x. And then we will exponentiate both those to clear the natural logs, giving us just absolute value y equals absolute value of x. And to solve for y, we should get y equals plus or minus absolute value of x. And which one do we want to choose there? We want the positive or the negative absolute value of x?
Positive.
We want the positive one, specifically because we are looking at x equals 2. So note that because x equals 2, we'll choose just the absolute value of x. And this should only be for 0 to infinity, because we have our discontinuity at 0 and x equals 2 follows on that side. And since we're just looking at y equals absolute value of x on the positive side, 0 to infinity, we could eliminate that absolute value because we know the x values are always going to be positive and just call it y equals x, but this is also fine. I would take either one. Good, any questions with that? All right. You guys want to do one on your own? All right. I'll give you 2 or 3 minutes here to work through this one. Ready, go. All right, so our first step here was to separate the variables. So dy over y plus 5 equals x plus 2 dx. Hopefully that's what you started with. The dy over y plus 5 is a simple u sub, u equals y plus 5. And then dy is just du, so it just ends up being natural, like absolute value y plus 5. X squared over 2 plus 2x plus your constant. Everybody get that far without any issues, hopefully? All right. And then y equals 1 gives us natural log 6, x equals 0 just gives us c over here. So now we're at natural log absolute value y plus 5 equals x squared over 2 plus 2x plus ln 6. And then we exponentiate both sides to clear off the natural log, giving us absolute value y plus 5 equals, and then over here, we're going to always use exponent rules if there is a constant with a natural log up there in the exponent. Like this, right? E to the a, we'll call that x squared over 2 plus 2x is a, plus b can be separated as e to the a times e to the b using exponent rules. And e to the ln 6 is just 6. So we've got absolute value y plus 5 is 6e to the x squared over 2 plus 2x. Good or no? And we'll clear off the absolute value with a plus or minus. And we get negative 5 plus or minus 6e to the x squared over 2 plus 2x. And then we have to choose one or the other. So we choose the plus or we choose the minus. Based on this initial condition, which one do we need to choose? We need the plus or do we need the minus? Yep, we need the plus, right? If we use the minus, we'd end up getting negative 11. Plus gives us the 1 that we need to get. So negative 5 plus 6e to the x squared over 2 plus 2x. And our interval on which this is valid should be what? Should be negative infinity to infinity, right? Every x value that we can plug, or we can plug any x value into this. Good? Or no? Adrian, it's valid for all values of x because there's no, there's no values of x that you can't plug into it, right? Right from the beginning, x squared over 2 plus 2x. When we integrated, you can evaluate that in the x value, right? But if you also look through at the final one, right, you can still do x squared over 2 plus 2x anything, e to any power 6 times that, and negative 5 plus that. No, we're not concerned about restrictions on the y values. We're only concerned about restrictions on the x values. So, there's lots of functions that have restrictions on the y values, but we don't talk about those restrictions, right? You think about a function like y equals x squared. Y is always greater than or equal to 0, but we don't state that if we talked about the domain of that function. When we talk about the domain of it, we only talk about potential x values that have to be restricted. Does that make sense? Okay. Cool. Any other questions on that one? All right. Let's have you guys do this one as well. So if we got dy dx equals e to the x minus y, and y equals 2 when x equals 0, just to make sure we do all right to get started, what's the first step with this one to turn it into something we can make a separable differential equation out of?
e to the power x over e to the power y.
Yeah, use our exponent rules to make it e to the x over e to the y. And then I'll give you guys a minute or so here to work through this one and see what you get. Sound good? Just a minute or two here. Ready, go. So e to the y dy equals e to the x dx, yeah? Integrate both sides to get e to the y equals e to the x plus c, and then plug in your values. So e squared equals e to the 0 plus c, or c equals e squared minus 1. Everybody good with that? Okay. Giving us e to the y equals e to the x plus e squared minus 1, and all we have to do is take the natural log of both sides. And just make sure you don't put that natural log as an absolute value there. A lot of people start doing that because they just get used to integration where the natural log always has the absolute value on it, but this is just, we're taking the natural log of it, so there's no absolute value. And then any restrictions would be when e to the x plus e squared minus 1 is less than or equal to 0. Well, if we think about that, e squared minus 1 is positive, right? And e to the x is also positive, so we got a positive and a positive. So there's no restrictions on this either. Any questions or issues there? All right, cool. So that's about it here for the basics of separable differential equations. We're going to now talk about exponential growth and decay just for a couple minutes here. We'll get through that today. Looks like we'll have to do logistic growth tomorrow, but those are the two different little applications of separable differential equations that we're going to deal with. So the first, like we said, is exponential growth and decay. So if we have the change in a variable, so dy dt, the change in y, is proportional, so it's got some constant in it, right? To the amount of that same variable, dy dt equals k times y, or if we had dx dt equals kx, or d theta dt equals k theta, we call this exponential change, right? That's how this is defined. This is exponential change, and we've talked about exponential change last year, and should know what that is. Like we talked about the growth rate of bacteria in a petri dish, or the decay of radioactive particle or radioactive nuclei in some sort of radioactive element. Those are all exponential growth and decay, right? And so the reason why this is exponential decay is if you solve this differential equation, you get an exponential function. And so let's do that. If we do dy over y equals k times dt, and then integrate both sides, the left-hand side should be natural log absolute value y, and the right-hand side should be k times t plus some constant. And when we exponentiate it, we end up with the absolute value of y is equal to e to the kt times e to the c. And we could make that a plus or a minus if we wanted to, but we know that if we're talking about the amount of something that we have present, whether it's radioactive nuclei, or if it's bacteria multiplying in a petri dish, or rabbits breeding in the wild, or whatever, we're never going to have a negative number of those things, so the negative doesn't really matter. So we just have y equals, we'll just call e to the c a for now. We get this nice little equation here. And what is the a value equal to? Anybody remember what the a value is equal to? Yeah, the a should be the initial or the starting amount, and we'll prove that right now too in just a second, but this is your initial amount. And we'll note that this is an exponential equation, right? E to the kt, right? The amount of y is equal to the initial amount times e, right? Our exponential constant, Euler's constant, times some or to the power of some constant times the amount of time. And that's by definition what an exponential function is. And so if we go in, and we'll do it here, we'll do it here, make a new page. If we go in and take that equation, a e to the kt, and let t equals 0. If t equals 0, then y is the initial amount of y. So we would replace the y with y naught equals a e to the k times 0. K times 0 is 0. E to the 0 is 1, and so we just end up with k equals y naught, and that gives us the equation you are most probably familiar with, y equals y naught e to the kt. You will not have to really solve any exponential growth or decay problems on the AP test, but you do need to know that that differential equation dy dt equals k times y, where the amount of one variable is proportional to its change, that yields the exponential growth or decay formula. And this can be seen in, interest, like bank interest. Those are both exponential and come from a differential equation that is the amount is proportional to the amount that you have of it. And our k, our constant of k, is always positive if it's growing, and if the thing is decaying or getting less, our value of k is always a negative value. We always put a negative in front of it. We technically try to define k as just some positive constant, and then we just deal with putting a negative onto it if we know that the thing is decreasing. Okay. Good or no? And you don't need to know those formulas either. Just know that they exist and know that they come from a differential equation. All right, so the one thing we will do with this is we're going to prove what the half-life is equal to. And so in order to do that, we're going to say that our final amount, our y final, is equal to half of what we started with, because that's what we do, right? Is we, if we want to find out how long it takes for half of the stuff to decay, we just need to have our final amount be half of what we started with. And so if we do that, we should be able to cancel out the y naughts and just get e to the negative kt equals 1/2. Note that the k value itself is going to be positive. We just put a negative in front of it to indicate that it's decaying. And so now we'll take the natural log of both sides, which ought to give us just negative kt equals natural log of 1/2. And normally we'll rewrite natural log of 1/2 as natural log of 1 minus natural log of 2, with natural log of 1 equaling 0. So we've got negative kt equals negative natural log of 2. For our half-life, t is equal to the natural log of 2 over k. And so if you were ever asked for the half-life of any radioactive element, it's always equal to the natural log of 2 divided by whatever that exponential decay constant is. And the number you're dividing by will always be a positive number. Good or no? All right. So just real quickly, we'll do one of these as easy as could possibly be here. We are looking at the decay of this samarium 151, which has the differential equation dy dt equals negative 0.0077y. So it tells us that our k value is 0.0077. The negative in front just indicates that it's decaying, not growing. And if we want to find the half-life, it should just be the natural log of 2 divided by that, which gives us what? How many years? Sounds good to me. And that's that. Any questions on that?